Hello. Hello.
Hello.
Okay, so let's start with the class today. So we have our last weekly tutorial session, that is the discussion for the week 8 classes. So in this we'll be have discussing two case studies regarding the life cycle assessment, and we'll have a detailed analysis of the life cycle inventory as well as the life cycle impact assessment for the two cases that we discuss. And after that, we'll be having our weekly question answer or the weekly tutorial session. And so, yeah, let's get started. So, first case study is the technological and life cycle assessment of composting and AD odor control technologies. So, basically, this study is done to understand the life cycle assessment of the composting process and the odor generation due to the decomposition of the waste. So we all know that municipal solid waste management is an essential service which includes the disposal, recycling, and the organics processing. And for a typical municipality in Canada, the organic waste makes up to 40% of the municipal or the residential waste stream. So this case study was done in Canada, and here the organic waste, like out of the total municipal solid waste, organic waste was 40%. So more and more municipalities are implementing options for processing the organic waste, which includes both composting and anaerobic digestion. So here, out of the total organic municipal solid waste, 40% was your organic waste. And we are for the processing of this waste, we are going for two options. First is your composting process, that is dumping this waste in. First process is the composting process, which includes the dumping is burying of this waste under the soil, and the second process is anaerobic digestion, which means decomposition of this waste in the absence of air. Uh, Pooja, if you may confirm that am I audible to you guys? Hello. Okay, so let's proceed further. So, although there have been great technological improvements, the odor from composting and anaerobic digestion facilities continues to be a major issue. We all know that during the process of decomposition or the composting, when the waste is getting decomposed, generates a lot of odor problem, and that is why some complaints often bring legal problems, and in some cases, closure of the facilities. Due to this odor problem, in some cases, the closure of the facilities is also done. So, for organic waste management, odor control is one of the most expensive and environmentally impactful components. So, therefore, a good understanding of the different technologies available for odor control is crucial. So, why this odor is still a problem? Like, why aren't able to solve this odor problem? Because this odor is resulted from many different compounds that interact together in very complex ways. So, some of the common sources of odor include the hydrogen sulfide. It has a very pungent smell. So, hydrogen sulfide, then we have organic sulfur, then organic sulfides, then ammonia, amines, fatty acids, aromatics, methyl ethyl ketone, and terpenes. So these are the agents that cause odor during the decomposition of the organic waste. Now coming towards the objective and scope of this project. So what were the objectives and the scope of this project? So the aim of the project was twofold. Basically, this project was done in two different phases. The phase one included the identification and technological assessment of the odor control technologies for municipal solid waste organics. And the phase two included the life cycle assessment of selected odor control technologies based on phase one results. So phase one was technological assessment. So different odor control technologies or methods. These include your biofilter, then activated carbon adsorption, then packed bed wet scrubbers, then fine mist wet scrubbers, thermal oxidation, then oxidizing chemicals, and then masking agents. So these are some of the odor control methods that we'll be comparing. And among all these methods, we'll try to find out the suitable method, and then we'll move towards our phase two, like a life cycle assessment of the selected odor control technologies based on the phase one results. So first one is biofilters. So these filters use microorganisms to degrade and destroy the odor compounds. So here, see, this is your inlet where foul air is injected along with the steam, and then we have a heat exchanger, and then this air moves upward through this perforated supported plate, and this is some kind of bulk media filter bed. This is your filter bed. It has small spaces, so the air tries to move upward, and along with that the impurities present in the air gets trapped in this filter bed, and this filter is moistened with the help of these spray, this water sprinkler. This is your water sprinkler that moistens the filter, and this moist filter starts developing some microorganisms, and then these microorganisms try to degrade the odor compounds, and clean air is released from this exhaust. So this is your mechanism of biofilters. Then we have activated carbon. So these are, we all know that activated carbon is a very good adsorbent. We use it in different processes. So the odorous compounds, these are removed by the adsorption on activated carbon. So that why this is a very good adsorbent, because it has a very high surface area, that is close to 1400 meters squares per gram of the material. So the gases and the chemicals, they get trapped inside the pores of this activated carbon, and that is how they are removed from the airstream. Then we have packed fine bed mist wet scrubbers. So the mechanism is almost same, like we have, this is the inlet for the odorous air, and these are the screens from which the air passes, and above it we have packing media and spray nozzle that sprays the water, and here we have a recirculation pump also that that recirculates this spent chemical solution, or recirculates this makeup solution through this spray nozzle, and the spent chemical solution, which is like contaminated solution containing the all the chemicals or the odor causing compounds, gets out from the system from these nozzle. So this is the mechanism of packed bed or fine mist wet scrubbers. So this washes odorous compounds from the air stream into liquid scrubbing solution. Then we have some thermal oxidizers which destroy the odorous compound in the air by heating it to a temperature between 1300 to 1600 degree Fahrenheit. Some chemical oxidization can also be done. For example, some of the chemicals like potassium permanganate, which is a very strong oxidizing agent. So it can be used to like these chemicals react with odor causing compounds to form odor free compounds. Then we have some masking agents. These are the chemical agents used to mask the odorous compound, that is patented compounds or the essential oils. So for the technological assessment, the factors that we considered are the chemical and operation and maintenance costs, volume of airflow handled, odor units removal efficiency, the reliability of the process, the space requirement, the chemical and media usage, the energy usage, and the water usage. So all these factors were assessed for the technological assessment of all these methods. And this is a table that shows us the technological assessment of all these factors like for the biofilters, activated carbon, then packed tower wet scrubbers, fine mist wet scrubbers, thermal oxidizers, oxidization chemicals, and masking agents. So, for example, like for biofilters, the capital cost is moderate, but the odor unit removal can be more than 90%. So it has a very high efficiency. And like it has a high efficiency, but for activated carbon the efficiency is more than 99%, so that is very high. So and its reliability is also excellent, and the capital cost is moderate operation, but its operation and maintenance cost is high, whereas for biofilters operation maintenance cost is low. So these are all the parameters which are used to compare all the methods. And what are the key findings of the assessment? So, from a technological efficiency, usability, and cost perspective, the biofilters are a preferred option. And packed bed wet scrubbers also function well in composting and AD facilities, that is anaerobic digestion facilities, especially for more concentrated air streams. Then fine mist wet scrubbers are not a preferred choice due to higher capital and operating costs. So we compared these methods also from an economic point of view. Then carbon adsorption can be useful, but its applicability is limited to odor streams where ammonia is not produced. Then we have thermal oxidizers, which are not practical due to high cost and use of fossil fuels and potential production of SOx and NOx. So we are trying to remove odor from the air stream, but on the other hand, we are releasing some air pollutants into the atmosphere. So that is not the correct method to remove something, because in one hand we are removing the odor, but in the other hand we are creating some air pollutants as well. So this method is generally not preferred. Then oxidizing agents or the masking agents can be used as a part of odor management plan, but not effective as individual methods. Now coming towards the technologies for LCA. So looking at organics processing facilities across Ontario, it is found that biofilters are only odor control system used. So generally we try to use biofilters, and these are the only odor control system that is used. And then Guelph and Peel uses synthetic media, while Hamilton and London use organic wood chips media. Both systems have odor removal efficiency of 90%, which is similar to packed bed wet scrubber system. Thus, based on results of assessment looking at industry practices, three technologies were chosen for LCA. First is synthetic media biofilter, then we have wood chip media biofilter, and then we have packed bed wet scrubber system. So these are the filter media. Like the synthetic media biofilter has the filter media which is made up of synthetic materials, and for wood chip media biofilter the media filter was made up of the wooden chips. So coming towards the phase two, like we have formulated these three filter systems. Now we'll be doing LC of all these three methods, and we'll try to find out which is the most efficient way of the removing the odor from the system. So coming towards phase two of the life cycle assessment. Now the goal and scope of the LCA, like we need to define the goal and scope of the LCA. So LCA takes into account materials of construction from extraction that includes transportation, energy usage, water and chemical usage, and landfilling and recycling during decommissioning phase. SEMA Pro 8 software was used with its EcoInvent database processes, and all three technologies assessed over 15-year period since it is expected life of synthetic inorganic media. Now, what are the system boundaries and the functional units? So, the geographical boundary of analysis is considered to be region of Ontario, and facility in Gulf process 30,000 tons per year of organic waste, whereas the facility in Hamilton that processes 70,000 tons per year of organic waste. So, all the materials or chemical, water, and energy uses for all the system that is scaled to 1,000 tons per year, and the boundary for each system only includes odor removal system and not consider pre-treatment of pre-scrubbing of air or pre-scrubbing of air. Since all the three systems have a comparable odor removal efficiency, the effect of treated air is not considered in this study. Now, what coming towards the data collection part, like the first process in the life cycle assessment is the data collection of data. So the data for biofilters collected from facility in Gulf, which uses synthetic media, and facility in Hamilton, which uses wood chip media, and data for the packed bed wet scrubber system was collected from literature and previous studies and downscaled to 1,000 tons per year. Now, what are the assumptions and limitations of this study? So, only materials, chemicals, and equipment with significant quantities were included in the study. The small components such as screws, bolts, wiring, etc., were considered to have a negligible effect. In terms of scaling data, it was assumed economies of scale have a negligible effect, and it was assumed that the treated air based on 1,000 tons per year would have negligible environmental effects when compared to the effect of materials, energy, water, and chemical usage, and the reasonable assumptions based on common knowledge were made in the case of missing data. The database made use of European and world values. Now, what is the key data and the inventories? So, the biofilter systems were divided into five sub-assemblies: building frame, the filter media, then fan suction system, which sucks the air from the inlet. Then we have water sprinkler system on the top of the filter media, then control and monitoring system. Then the packed bed wet scrubber system was divided into five assemblies, for example, which are first is the outer shell, then we had some packing material, then spray solution system and fan suction system, and last is the control and monitoring system. So key data and inventory. So this is the data for all the three processes. The biofilter comprised of three concrete cells, three suction fans, and with 810-meter cube of synthetic media. And this synthetic media was comprised of silica and alumina coated with mixture of ferrite, organic carbon, alkaline buffer, and hydrophobic chemical. Biofilter at Hamilton facility comprised of one big concrete cell. Here we had three concrete cells. Here we had one big concrete cell. Here we had three suction fans, and here we had four fans at 1200 meter cube of with wood chips. The synthetic media was 810 meter cube, and these are changed for every 2 years. Then the packed bed system comprised of fiberglass interlock saddle packing material and uses sodium hypochlorite and sodium hydroxide as scrubbing material chemicals. The impact categories, the for this LCA, 12 impact categories were assessed. First is the cumulative energy demand. Second is the climate change. Third is human toxicity. Then photochemical oxidant formation. Then metal depletion. Then fossil depletion. Then we had terrestrial acidification. Then freshwater eutrophication. Then we had marine eutrophication and terrestrial ecotoxicity, freshwater ecotoxicity, and marine ecotoxicity. So, coming towards the LCA results, so these are the direct and indirect cumulative energy demand. So, for the we can clearly observe that for the The cumulative energy demand was maximum for the biofilter system for consisting of inorganic filter material. And this is the breakdown of the inorganic biofilters cumulative energy demand, that is for that which used your silica and alumina and the synthetic media. So this is the cumulative energy demand where maximum part is used by the electricity market. Then we had aluminum sulfate powder, then polyvinyl chloride, then concrete, then for blower and heat exchange unit, and the last is for the remaining process. And this is the breakdown of wood chip biofilter cumulative energy demand, and this is the breakdown of packed bed cumulative energy demand. Now coming towards the characterization and normalization. So characterization scales the result by percentage based on the highest impact, and normalization is done by dividing the impact category by the reference. A reference value can be found by looking at the average environmental load in a country or region over a year and dividing by the number of people. So this is the characterization of climate change, human toxicity, the photochemical oxidant formation, the metal depletion, and the fossil depletion in percentage. These all the values are in percentage, and the maximum impact was given to your biofilter system for inorganic material, and the minimum impact was observed in packed bed wet scrubber system. Here normalization is done for the climate, human toxicity, photochemical, metal and fossil depletion. Same is the characterization and normalization for other parameters. Now the impacts of concern. So the based on the figures, the impact of concerns are the metal depletion, fossil depletion, human toxicity, freshwater eutrophication, and marine ecotoxicity. And this is the synthetic biofilter LCA breakdown for all these impacts of concern. And these are all the breakdowns for all the impacts of concern. Now coming towards the key impacts, that is climate change. So although the climate change impact is low, but it is considered because it is always of the concern. Fan suction system is responsible for most of the climate change effects for all the three odor control systems, and the electricity demand for the fan suction system is responsible for more than 80% of the climate change for effects for each system. Now coming towards the key impacts, that is metal and fossil depletion. So fan suction system is a major contributor to fossil fuel depletion for all the three systems, particularly 24/7 electricity usage. The metal depletion impact of wood chip and packed bed system is fairly low, while the synthetic biofilter system has a fairly high impact. More than 90% of this impact is associated with ferrite used to manufacture the synthetic media. Now, for the freshwater eutrophication and marine ecotoxicity, the inorganic and wood chip biofilter systems have a fairly high freshwater eutrophication and marine ecotoxicity impact. And the major contributor for both systems is the 24/7 electricity usage along associated with the fan suction system. So these are the key impacts for the human toxicity. So for all the impact categories, the inorganic media biofilter had the highest impact, followed by the wood chip biofilter system, and the packed bed system has the smallest impact for all the categories. So the synthetic media showed higher impact level than the wood chip media, even though the synthetic media had the lifespan of 15 years and wood chip media had to be replaced every 2 years. So the major contributing factor for all the impact categories was the higher electricity usage that is associated with using a bigger fan suction system for the biofilters as compared to a smaller system used for the packed bed system. And the biofilter systems have to draw odorous air through the larger surface area of material as compared to packed bed wet system, which uses single industrial fan. The inorganic media and biofilter was primary cause of high metal depletion impact. The synthetic media is coated with a ferrite solution. Now coming towards the conclusion and the recommendations. So choosing system based on operational parameters, the biofilter systems were the recommended choice. Looking at the operation and maintenance and ease of operation, the inorganic system is the preferred choice over wood chip system because media does not have to be changed often. In terms of system with lowest environmental impact, the clear choice is packed bed system based on LCA. Thus, choice of system depends on what criteria is of importance. That is, either whether we are concerned about the cost or the environmental impact or the system operation. So this is the conclusion that we got for all the three uh, factors that we needed to consider. That is the cost, system operation, and the environmental impact. It is very clear that the inorganic biofilter is the most efficient in terms of the system operation, and the packed bed wet scrubber is the least efficient. And in terms of cost, the organic biofilter is the most efficient. And in terms of the environmental impact, the packed bed wet scrubber was the most efficient. Mm. Coming towards the another case study, that is the kerosene lamp and the solar lamp. So we needed to compare the usage or the we need to compare which is more efficient. That is whether we should use a kerosene lamp or a solar lamp. So the goal is to compare a kerosene lamp to a solar powered lamp to determine a favorable solution. So describing the function and the functional unit, here the function is to provide adequate lighting for reading and writing. For this is the function for both the lamps, either the kerosene or the solar lamp. And here we have defined the functional unit as more than 100 lumens for 4 hours every day for 10 years. So the scope defining, first we have defined the goal of and scope of the, now coming towards the scope of this study. So like every LCA study starts with the first thing is goal and scope of the study, and second is function and functional unit. So we have defined the goal. Goal is to provide the goal of this study is to compare a kerosene lamp to a solar lamp to determine a favorable solution. So our goal is to compare both lamps. And what is the scope of this study? So the scope of this study is from cradle to gate, from the raw material acquisition towards material processing, then manufacture and assembly, and then use and service. We are not concerned about the retirement and recovery or the treatment disposal process. So this is your cradle to gate study. And the function and functional unit is function is to provide light, right? And our functional unit is more than 100 lumens, 4 hours per day, right? And for kitna? 10 years. So we have defined the goal and scope of the study, then the function and functional unit. Now, these are some of the components. Like first we'll start with the solar power lamp. So these are the some of the components of the solar lamp. The outer casing is made up of polyethylene material. Then we have some nickel battery inserted inside this, which and for the operation of this solar lamp we have a PCB, that is printed circuit board. Then some steel screws are there and also a steel handle. You can clearly see that this steel handle is there. Then this is a solar panel inserted installed on the top of this lamp. Then LED light is there. which is installed inside this lamp, which gives us the lighting. And then this lower casing is made up of polypropylene. So coming towards the assumptions, so the assumptions for this study is the usable life of this lamp is 10 years. It is assembled in Shenzhen or China, and it is distributed in Tanzania or Africa. So after assembly, it is transported to Africa and it is distributed and used there only. So from where are we importing all the parts? Like the assembly is done in China, but all the components are manufactured in different places. So the polypropylene is like imported from Mitsui Corporation Limited from Japan. Then polyethylene is polyethylene is got from Yongtuo Chemicals Corporation Limited, which is in China. Then this is the process of polymerization for the polypropylene and polyethylene. And then the PCB boards are uh, like the PCB boards we get from Zhuhai Westpride Technology Limited from China only. And the photovoltaic cell that we get from Linhai, Xi'an, China. The LED light that is installed inside this lamp is got from the Shenzhen Easter Battery Corporation. Sorry, the LED light is got from the Lightning Optoelectronic Technologies Corporation that is in Shenzhen, Guanghan, China. And the battery is also got from Shenzhen Easter Battery Corporation Limited. Both are in China only. So the impact from processing materials. So these are the impacts that were that we had from during the processing of all these materials before the manufacturing phase, like during the raw material acquisition phase. These are all the impacts that were generated, like CO2, CFCs, NMVOCs, PM10, then SO2, then different all the different impacts that are per kg of contaminant are given in this table. Now, this is the total traveling distance for each of the component of this lamp, and which is assembled in Shenzhen in China. Like the polypropylene or the polyethylene travels for 1964 kilometers, then the solar panel travels for 1366 kilometers to reach s- this is polyethylene comes for 1964 kilometers, and polypropylene comes for 3864 kilometers, if I'm not wrong. Let me confirm. Yeah, polyethylene and polypropylene. Okay, so this is your polyethylene. This is your polypropylene. This is your solar panel, battery, LED, and this is your PCB. So this is a total for all the components. What all mass is required is given in this table, and the distance in kilometers that the components needed to be traveling, and what is the transportation method that is involved. That all these values are given in this table only. So these are the impacts that are that we have from the transportation. Like we use two types of transportation methods. First is your lorry or truck, and second we had a freightliner, that is Different impacts of all these transportation categories were included, like climate change, ozone depletion, human toxicity, photochemical oxidant formation, particulate matter formation. Then we had ionizing radiation, terrestrial acidification, freshwater eutrophication, marine eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, then marine ecotoxicity, then agricultural land occupation, then urban land occupation, then natural land transformation, then water depletion, metal depletion, or the fossil depletion. So these are all the impacts during for the because of the transportation process. Now coming towards the second part, that is processing of these materials. So the processing of materials included two things. That is, first is your metal working machine operation, and second we had injection molding for polyethylene and polypropylene. So this steel is used to this metal working machine operation was used to manufacture screws, and second we had metal handle for the lamp. And this injection molding was used to formulate the upper and lower body or casing for the lamp. Then we had the assembly of all these materials, and then this lamp, after the assembly, goes for packaging. And during the packaging, we use two types of materials, that is cardboard, the cardboard box inside which we used to place our finished product, and also polystyrene, that the thermocol that we like use for fixing that lamp inside the cardboard box, so that any it doesn't get damaged while transportation. So these are all the impacts that are generated during the metal working machine operation. Then these are the impacts during injection molding, and we can clearly observe that the maximum impact is caused due to this climate change, caused in this climate change due to all the operations. Then these are the major impact categories for all the components that were used. Like the battery had the maximum human toxicity levels, followed by the circuit boards and the solar cell. And the solar cell has the maximum climate change effect per kg of contaminant. And the minimum effect was observed for like these screws and the polyethylene part. These are the minor impact categories. So the major impact categories included climate change, that is CO2 equivalent. Then we had human toxicity. Then we had ionizing radiation, agricultural land occupation, metal depletion, and fossil depletion. And the minor impact categories, these include ozone depletion, photochemical oxidant formation, then we had particulate matter formation, then terrestrial acidification, then freshwater eutrophication, then marine eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, marine ecotoxicity, urban land occupation, natural land transformation, and water depletion. So these are the all the major and minor impact categories. Now coming towards the kerosene lamp. So some of the assumptions that are made for the kerosene lamp, these include uh, there's a tin box inside which is used to form the kerosene lamp. So first we have a box which has a usable life of 2 years, and then it is 1 mm thick and it can be recycled. And it was formulated in Nairobi, Kenya. And then we had cotton wick, that is 3/4 inches in diameter, and it also has a usable life of 2 years, and it is a processed product. So for every 10 gram of woven cotton wick, like for the given functional unit, we needed 10 grams of woven cotton wick, 5 grams of the tin container, and 5.5 liters, having 5.5 liters capacity. And then kerosene is used as a fuel. So now coming towards the transportation impact. So the component like tin, its mass is 0.665 kgs and the distance of transportation is 352 kilometers. Same is for the cotton wick, and the mass is 10 grams only. The number of trips included were five trips each, and the tons of per into multiplied by kilometers is this much. So the load of total land transportation is 1.1704 tons into kilometers. And these are all the impacts of transportation that are involved for the kerosene lamp. And for cotton wick, these are the impact categories that we considered. And these are the impact categories for the kerosene fuel. So, and incorporating both the impact categories, that is for cotton wick and the kerosene fuel, we get the kerosene lamp impact categories. And we can clearly see the maximum impact is on fossil depletion because the kerosene fuel is formulated in kerosene is a fossil fuel, and thus it has the maximum impact on the fossil depletion. So the kerosene uses, so what amount of kerosene is are we using? So volume of kerosene used per year household is 60 liters, and the volume, so for 10 years we use the total volume of kerosene as 600 liters. The mass density of kerosene is 750, and the molar mass of kerosene is 170.34 grams per mole. Thus, the molar of carbon dioxide is 44.01 grams per mole. So we needed to convert this kerosene into total amount of CO2. So the molar density of kerosene comes out to be mass divided by molar mass. So it comes out to be 4402.96 moles per meter cube. Then moles of kerosene consumed will be equals to molar density into volume of kerosene used. So like the molar density is 4402.96 moles per meter cube, and the volume of total volume of kerosene used is zero point 0.6 meter cube, right? So we'll multiply this by 0.6 meter cube. We get 2641.8 moles of kerosene. So for CO2 generation, kerosene consumption into stoichiometric ratio, like conversion of this amount of kerosene into CO2, we multiplied this by the stoichiometric ratio. So 1 mole of kerosene is equals to 12 moles of CO2. Like we can see this for for the combustion of kerosene, 1 mole of kerosene forms 12 moles of CO2. During the complete combustion, 1 mole of kerosene during combustion gives out 12 moles of CO2. So for 1 mole of C, so to total for 264.1 mole of kerosene, 2641, this is, so for 2641.8 moles of kerosene, total CO2 generated will be 2641.8 multiplied by 12, right? So this comes out to be 31700 moles of CO2. Now, converting this CO2 into total mass of CO2 generated. So, mass of CO2 generated will be computed by multiplying this with the molar mass of CO2, that is 31700 moles of CO2 into molar mass of CO2 is 44.01 grams per mole. And converting this into kg, we divide it by 1000, right? To convert these grams into kg. So we get 1395 kg of CO2. So this is the mass of CO2 generated per household. And when we multiply this by the total number of households, we get the total amount of CO2 generated by burning of this kerosene. So this is the comparison table that is the characterization of the environmental impacts for the solar lantern as well as the kerosene lamp. And this is the normalization of the environmental impacts. So 600 million people already use the kerosene lamps for the lighting, and the CO2 produced from one Shenzhen Power PS solar lamp is equals to 3.315 kgs of CO2, while for kerosene lamp functional unit, we get 1683.4 kgs of CO2. So the total difference in CO2 per functional unit is 1680 kg of CO2. So for 600 million people, we like that is for 4 people per household. So to calculate the kerosene per household, we got 252 million 12,750 tons of CO2. That is the total amount of CO2 that was generated. That is the difference of CO2 from both the device for both the units that we were comparing. So it is clearly observed that using a solar lighting is a better alternative for the kerosene lamp because it generates a large amount of CO2 during its combustion. So with this, we come to the end of this module, and now we'll be having a quick discussion about the last year's assignment questions. So I'll just quickly get into that. Second, just quickly from that assignment. Okay. So we'll be having a assignment for week 8. Okay. So coming towards the first question, the first question is what is the aim of endpoint indicator? Let me quickly write the options. To indicate human to indicate ecosystem damage. Only key point is to indicate human health and ecosystem damage. And the last one is none of the above. So during our life cycle impact assessment part, we had two types of indicators. Like one was the midpoint indicator and the other were endpoint indicators. So we discussed about the aim of the endpoint indicators. So it will be the endpoint indicators. The major aim of the endpoint indicator was to indicate the human health and the ecosystem damage. Like we were concerned about both the factors, right? Now, coming towards the second question, we have which one of the following indicator is used to calculate the immediate impact on environment? Endpoint, midpoint, first point. So the another thing that was related to the midpoint and endpoint indicators was the duration of the impact, to calculate the immediate impacts or to consider the immediate impacts caused by certain activities, we use the midpoint indicators, and to consider the long-term impacts, we use the endpoint indicators. So clearly, to understand the immediate impact on the environment, we try to find out the midpoint indicators. Now, coming towards the third question. Okay, so just a second. Okay, so the third question is, what are the protective measures that have already been taken to protect ozone layer? So first is Kyoto Protocol, second is deindustrialization. Third is CFC, phased out refrigerator. And fourth is regular monitoring of ozone concentration. So, among all these terms, what are the protective measures that have already been taken to protect the ozone layer? So, we know that the Kyoto Protocol was adopted to control the ozone emissions. And second is the CFC phase out refrigerator that has been formulated to control the ozone, uh, to protect the ozone layers and to reduce the emissions of the CFCs. Now, fourth question. What are the major global warming causing gases? Methane, ozone, sulfur dioxide, and D is carbon dioxide. So, among these, the major global warming causing gases are methane and carbon dioxide. Coming towards the fifth question, the AC method is a science-based indicator. It's for human and ecosystem monitoring. So it is true or false. So the Tracy method is a science-based indicator set for the human and ecosystem monitoring. So this statement is true. So coming towards the next statement, potency factors are used to calculate the degree to which the inventory elements contribute to environmental impacts. So the potency factors are used to calculate the degree to which the inventory elements contribute to environmental impacts. So this statement is true. Coming towards the seventh question, packed bed reactor uses microorganisms to degrade and destroy odor causing compounds. So, which reactor use these microorganisms to degrade and destroy odor-causing compounds? We discussed in the first case study. So, biofilters were there who incorporated the use of microorganisms to destroy the odor-causing compounds. So, instead of this packed bed reactor, the correct answer is biofilters. So, this statement is false. So apart from these 7 questions, I have 3 numerical questions, which I'll just incorporate after this class because I don't know somehow I missed those questions. I don't have them right now. So I'll just write those questions along with their solutions. So 3 numerical questions will also be added. And with this, we come to the end of this module as well as this course. And yeah, so feel free to send me your doubts with you guys have my email ID as well. So try to send your doubts from the email and wish you very good luck for the examination. So thank you so much, guys. Good luck for your examination. And yeah, I'll just add those 3 questions with this, and then after that I'll just um, upload this lecture onto the Google Drive. So thank you so much.